let us continue with what we are discussing. We are discussing what you remember. That's what state function and path function. So continue. Lecture 3. Lecture 3. State function, and function continue. And path functions continue. So we had a nice observation yesterday that thermodynamics and mathematics, means calculus, bound together. They go hand in hand. For example, what I said, you can read very nice statement that state functions, okay, differential of a state function is actually perfect differential. So state function differential is actually differential d of state function is d of state function. State function is a thermodynamic and is perfect differential is calculus or mathematics. So they are related. Likewise, d of path function is imperfect differential. This I said yesterday. So today actually I continue on this so that I will today consider one function, one expression PD. I can continue. PD, we consider PDB. Is it a perfect differential? Is the PDB a perfect differential? This question comes. Okay, now what is PDB actually? This is actually work done. This is actually known for some reason I consider PDB known BW is PDB. Work done is PDB. This is reversible. Goal is reversible. But don't worry about this reversible now. Reversible process. But don't worry. Just this is work interaction. We know the work interaction must not be a perfect differential. It should not be a perfect differential. But let us how to know whether it is perfect differential? I can try. What I taught you, PDB, can you write? I cannot write. I cannot write myself. You can write. If it is a constant pressure process, then it can get into dBV. But when you say it is a constant pressure process, that means you are defining the path. It is a path. If this path, constant pressure path, then it is okay, perfect differential. So this is the problem. So it is without defining the path, you cannot. So you have to define the path. So path dependent then. So it is actually by nature, by itself it is an imperfect differential. I will show you more on this. If it is, you know, it is actually, I am showing this. Check, examine this. And also, when you cannot write this, another thing I can add in. When you cannot write this D, you cannot integrate also. How will you integrate? If you cannot write this way, how will you integrate? You can integrate if the path is specified. Otherwise, you cannot. For example, we will try to integrate this. Alternatively, you take this. Another way, you cannot write D. The moment you can write this, you can integrate. If you cannot, you try to integrate. Well, yes, I will integrate, sir. Integrate P and D, how to integrate? Y dx. Who will be able to integrate? Unless the relationship between Y and X is known. Unless the relation between P and B is known, I cannot integrate. And when I know the relationship between P and B, that is the path. The relation of P and B is path dependent. If it is isothermal, one relation. PV is constant. If it is constant pressure, P is constant. P is constant. Constant volume. Okay, P is variable. B is constant. So path dependent. Adiabatic, there is another. All I will discuss later. It is not PV relation. Is not PV is constant. Rather than that, it is PV to the power gamma is constant. This I will show you later. So you clearly understand. I cannot integrate for the same reason. What is the reason? So this is not a perfect difference. But I will give you another example where you will see, sir, I can and we can. So you cannot. If you try, suppose you try, okay? Try actually. You say, suppose you don't want to give up. No, sir, I will try, sir. PV relationship don't. Okay, sir, very good. So I will try. Otherwise, see this ideal gas. The ideal gas. N RT by E dV. N RT by E dV. You twisted it. Suppose you thought that there will be remaining. Let us say. N R no problem. N R will be outside. Again dt. What's the relation? Depends upon the power. I got to integrate. Okay? Okay, so this you cannot integrate. Okay? But in contrast, since I am discussing this, I am giving you actually let me complete this first. So I consider this is the path and giving you the path 1 to 2. What is the path? Consider ideal gas in the system. Note here somewhere. Ideal gas system. Okay, is right here. Is what? Means you cannot. Is what? You cannot. Because it is not a perfect differential. It is somewhere. So it is not a perfect differential. Is the what? Even what? Means not a perfect differential. Not a perfect differential. Not a perfect. So shown number of ways. More I will show you. How many ways you can get this? That it is not perfect differential. So I am considering this with ideal gas right here. Ideal gas in the system. As system. So please 1 to 2. Suppose I am taking this ideal gas. This called starting state is P1. P1, P. Follow very closely. You will enter this. Okay. P2. We are going to state 2, which is P2, V2, P. That means it's an isothermal process. Reversible. Don't worry about this. But this is system moving from state 1 to state 2. Nothing else. Okay. And I will show you that to show this. Not a perfect difference. So next is what? Another this is 1A2. What is 1A2? 2 ways I am trying to get the system from state 1 to state 2. Two ways. This is the first way, isothermal. Another is I am giving you dropping this here and then I am giving double arrow to distinguish double arrow this part. What is the part? 1B2. 1B2 is part. It is a constant volume combined with constant pressure. But all the same, it is from 1 to 2. Initial 1, final 2. So 2 different ways. Now if I ask you, see, what is this? Integration PdV here. You first integration PdV, you know what is this? You know integration y dx is nothing but area under the curve. Area under the PV curve. This is integration area under the curve. So if this let us check. So I want to get this function integration PdV. See area under 1 is what and area under 1 PdV. But I am showing first one which will help you. This is, so I am writing here, okay, integration PDB under 1 B2 is what? Integration PDB 1 to B plus PDB. Okay, what is this? See, this is the 1 to B is a constant volume part. So it will be constant volume. Means this is 0. What is this? What is the PDB? This is nothing but P is nothing but what pressure? What is the fixed pressure here? P2. This is actually P2 pressure. Horizontal line. P2 against 20 is nothing but P is nothing but constant pressure process. P2 times. This is the result. This is the result. So area under the curve is what we have considered. What is the area under the curve? Area under this vertical line plus area under this horizontal line. Vertical line does produce any area? Vertical line any area? No. That side is 0. Makes sense? Makes sense. Constant volume. And this is there is area. What area? Head line. Cross hatchet. Okay. Then white. So this is the white. Then cross hatch white. And now again you start to get PDB again. PDB 1 into sit down. Good. 1 into is what? Tell me. This is the first option. This is what? Integration PDB, you know very well. 1 to 2. This is very famous and popular. But I will later on take up this also. But today is what? If you do this, this is please 1 to 2. Actually, is it? And see. Okay. But what is the path? Right? Path is what? Right? 1 A2, 1 A2, Asukana. Asukana. So what is the answer? Please you know perhaps. You can get there is outside, R outside is the Asukana outside. So in that TLN, we will be. No, A1 TLN E2 by B1 is not equal to A1 and A1 cancel is not equal to E2 minus 1 So work done in two cases different.
Sir, the PB
Yeah,
PB minus PB
sir, not equal to P2.
Sir, we
B1 minus B1, yeah. This one. So the first one. This is one.
yes, sir.
This is one. What is the work done? Work done in the first case? First case? P2 into P2 minus B1 easy to call. The second case? Second case. Again in the second case. In the second case, like in the second case. First case, first case. Two cases. Coming time and possibility. Don't distract me. Okay. So you see, analytically they are different. Clearly, one is this, the other side. You know what? Why you go for analytical graphically? You know area under the curve, and you easily distinguish differentiate area. In the first case, area is already shown, and the second case, I will introduce this one. What is the second case? Area area under the curve. How much it is? Area under up to this x-axis. You know potential up to the x-axis, then area. So it is area cross hatchet white. You write here it is what? Cross hatchet. Cross hatchet. Yellow. So what is area? So what is your comment? Here, this area to area same. Area same? No. This is smaller. This is additional this one. Larger. So you what to deduce? What you got? Like that? Sir, this integration of PDB varies with path. So integration of PDB varies with the path. That is, which is actually W. That is the integration of that means PDB is a that is PDB not this. But PDB is a imperfect differential. Imperfect differential. PDB is a you don't mind na? Less constant. Imperfect differential. What is PDB? That is DW. Reversible though, but DW is and differential. That means W is a W is a path function. Don't say DW is a path function. No, so control your language actually. DW is not path function. W. dy is a path function or state function. P, pressure is a state function. So dP is a perfect difference. Pressure is a function, state function. Pressure, volume, temperature. And any expression you are giving to verify whether it is perfect or imperfect. The first test is if you can write in this form. P, it helps. And it has not satisfied the test, or it has not passed the test. So it will be imperfect. So what nucleus is imperfect? Already stated. How many imperfect differentials are there? Path functions are there? How many?
So what can be into?
Two. Only. Happy? Okay. So this is one verification. Interesting question. In contrast, so this part is over. In contrast, next means you understand next. Okay, easily follow. Or next, in contrast, I'm giving you a problem. You will enjoy this problem. We try to crack this. In contrast is PDB plus VDB a perfect differential again. A perfect differential. Again question posed. Now not PDB is not, but PDB plus VDB. Is it a perfect differential? Is it? Answer is yes. Because I can yes it is. Why? PDB plus VDB is nothing but PDB. The right in the form PDB. You follow this fast, then you have less difficulty. So D anything. Then it is perfect difference. Now you see interesting. Now you say sir, you must pass other tests. What are the tests? Different path I will consider. Is the result same? At the result same, I will check some. Let us see, I'm doing that. I'm doing this part with the same problem. Problem between the same paths. So in this case, so this answer, then I'm taking integration of dBd, integration of dBd power dBd is what I want to do, whichever. Okay, this is what integration dBd 1 to 2, 1 to 2 in either case, 1 to 2. What is dBd means what? Previously, dB2 minus dB1 d2 so find the integration. It's integratable and it does not make a follow. It does not. So this answer does it change if I consider this path? This path I consider. What is the answer? b2 minus b1 1. So 1 to 2. What is dBd? So integration and calculus and thermodynamics. Okay. So you consider this 1 b2. So 1 to 2. So dBd integration is dB2 minus dB1. So whether it is through A or through B does not matter. Does not matter. Integration you understand. We say the root is 1 to 2. I know. It is equal to understand. That means this state has this state 1 has P1 pressure, volume V1 sir, T is the temperature sir, defined, state is defined. Also there is a PV sir, obviously sir. Obviously PV is also perfect differential, which is also a state property. PV is a state property, V is a state property. Why is PV not a state property? It is also a state property. PV sir, PV and here also, B2B2 is actually, PV is a state property. So, no problem, sir. So, see the difference. PDB is not, but PDB plus VDB is a state function, is a perfect difference, sir. So, this function. So, this is over. State function, path function over. Okay? I hope. Next is start. So, over. State function and path function over. Next topic is what? What is the third? Fourth. Introductory terminologies continue. 1, 2, 3. Fourth. Thank you. Fourth is what? Extensive and intensive property. What is the extensive property? State properties which are dependent on the extent, size of the system, which are dependent on the extent, size of the system. Intensive properties. As an example, let us give example. I take volume B mass, moles, this is volume, this is mass, moles, mass and moles goes, you know, M is the moles I am often using. Moles and mass same. Why? How you get from mole to mass? 1 mole is 1 gram mole. Gram mole, how many mass? How much mass? Times molecular weight. 1 gram mole of oxygen is 32 gram of oxygen. Very easy. Times molecular weight. Mole. So mass and moles. Another I'm giving you energy. Energy covers many things. There are 5 types of energy I have said, what I have said. That is internal energy, enthalpy. This will be discussed later, though, but just name. Internal energy, enthalpy, entropy, now what is the extensive over? Intensity. State properties. Which are not dependent. Which are not dependent. On the extent of the system. Example. Temperature, pressure, value, okay. Temperature, pressure. Then more important is very good. Intensity. Another is density. It is named by this. N is extensive. D is extensive, but N by D is not. N by D which is density, and symbol is rho. It's intensity. Similarly, molar energy. What is molar energy? Molar energy, any kind of energy. What? Nothing but energy per number of moles. Energy divided by moles. Molar energy is also intensity. So I will show you with a sketch, simple sketch, how to get this idea. Suppose this is a block of iron, metal block. It is running temperature T. This temperature T. Now, what I said, I cut it into 2 halves. Each half is what? Temperature. You cut into 2 halves. This is temperature T. Half. What temperature? Same temperature. Does not matter whether it is half or full. That is reason, that is the extensive property. Intensive property. And likewise, pressure. Pressure will be also. Whole room is 1 atmosphere, half of the room is 1 atmosphere. The quarter of the room is 1 atmosphere. Okay? Pressure. But another example I am taking, in contrast, consider this block. What is the mass? Mass of the block is M divided into M by. So it depends on the size. Mass is likewise volume. Okay? Mass likewise volume. Not Kelvin. Density of this block, this is the block. Plastic. So total of this block is what? What is the density mass? Density. And what is the half of this? Half of this. The density is mass, density is an heat capacity. Very important note here. Heat capacity. here, then what it will be? Yes, this side is extensive. Heat capacity extensive. Molar heat capacity. One more. Okay, molar. Note here. Just note. You want this note. Conventions. How we express intensity of conventions. Okay? What I am telling you, two ways. Extensive, I am showing you, and intensive. Two examples I am giving you that follow. Heat capacity. Property is what? Heat capacity. What? How to write this? One way to write capital Cp or Cp is constant pressure heat capacity. Heat capacity. Extensive. And then what is this intensive in the what? Another it is capital is uppercase. Uppercase Cp and which will be what? Lower case. What is the name of this? Tell me what is the name? Heat capacity. Or this is what? What's the name? Molar heat capacity. Molar heat. Remove this. Molar heat capacity. So what? Lower case, upper case. Okay. This is the thing I'm saying. When it is molar, what is the name of this? Just like but you use this. Total heat capacity. Total heat. Now another convention about heat capacity. As a right hand convention. I'm considering heat capacity is the property. Another convention heat capacity. With respect to heat capacity I am discussing. Heat capacity I am discussing. Let us clarify this. Important. And you may get mistakes better. Oh, another convention is no. Okay. Intensive is Cp. This one. Intensive Cp. That means this another convention. Okay. Convention 1. Convention 2. What is this? This is Cp. People right. Then what it will do? What it will give Cp and what it will be? Now it will be Cp. This is here. Unprimed. This is primed. Okay. So this is what? This is remember unprimed means molar. Prime means total. Lower case means molar. Upper case means total. Any combination. I will use, actually I tell you what I will use. You can use any, mostly I will use this. But when it comes to energy, I'm giving you. I will write what shall I write here. I will write free energy, gives free energy. Important. Gives free energy. What is symbol? Gives free energy. Again, I will do the same job. Extensive. Of this upper lower. So what you will tell me? Yes, G-star. Okay, and second one is what? It is G-star. It is G. And it will be what? G prime. I will. I actually prime I will use in most cases, prime and unprime. But in the heat capacity I am used to use lower. Don't mind. But here answer me, okay, suppose I am giving you, I am helping you. Heat capacity, this is just heat capacity or total. What's the unit? Unit very important. Unit very important for each term. Don't avoid, don't evade. humid. What's the humid I am giving? This is June. He is required to raise the bottle in this. She said, he is required to relax. The moment I said, June. He is required to raise the temperature of the body if you want it. So June per Kelvin. This is the body. This is the body. He is required to raise the temperature of it. Like a facility in your school. It is required to raise the temperature of the body to 1 degree. So it is Joule per Kelvin. So unit. I am writing here. Unit. This will help you. Joule per Kelvin. What's the unit here to say? What's the unit? This one. Joule. Correct. Joule per Kelvin per I'm giving you. Continue. What's your problem? Answer this. What is the name? Sukolan. Suppose this value unit, this value is 40. This example. This value is 40. Joule per Kelvin. This is the object. This is the specimen. Body. 40. City. What is this value? You have to answer. Back end question, I will answer. I will try to give you the clue. But my question is, this is 40 Joule per Kelvin. What is it? And you want to ask everything? What was it? Yes, 40 molecule and mole is Avogadro number. And 1 mole and gram is molecular weight. That is another issue. Remember, molecule and number of molecules and 1 mole. Mole is 1 mole. Mole means 1 mole. Avogadro number. Separated. And 1 gram mole and mass means gram. 1 gram mole and gram. Molecular weight. Molecular weight. Remember. Continue. Yes. Yes. 40. It is what? You will ask back, so what are the number of moles calculated? Now I am giving you 10 moles are there. Then, all set? This careful. I am very careful till the last day. Next is what? Equation of state. Here. Yes, sir. Follow this. Take some time. This is a relationship. Oh my God, just right. Have you noted one thing? That extensive temperature, intensive temperature, pressure, and volume, all are state functions. All state functions. Some state functions are intensive, some extensive. Yeah, don't say that our state function means intensive. Don't say it. Okay? So it is a relationship between properties. Now, a relationship of state properties which is satisfied by all states of the system does it interfere? And later I can't okay. Thank you. Activity. So, which is satisfied by all states of the systematic equation. Example, this is example. TB is NRT. What type of system is ideal gas? So, or any modes of ideal gas. Ideal gas as system. Okay, happy? Because it is always satisfied. If you are when it is nothing but RT. When N is 1. Okay. Now EB is RT. EB is NRT quantum vector where N is given. Now EB is RT. See how many variables involved? 3. When 3 variables involved, like say x plus 3y plus 4z is 7. What is this equation? What does this equation represent? So x plus 3y is 5. X plus 3y is 5 to represent straight line. Curve. 2xy means curve. Y square is 4x, parabola, 8x. Ellipse, curve. Circle. X square by square means it's a constant. X, y variable, 2 variables. Circle, 5 parabola, parabola. You are getting amused? What are gene? The gene something? Gene is. Okay. PV is. Now PV is actually is an equation of a plane surface. P means surface. Use plane. And 4 means x, y, z, t. Space, 4 dimension. Okay. So, sorry, 3 dimension. So this is actually 2 dimension. Okay. So this is equation of a plane or surface. I will spend some time on this. This is important. I will spend some time on this. I will show you how we will draw this equation of surface. You show it here in the DBT. DBT diagram. DBT I'm drawing. This is your this is the equation of surface. Okay. What is that? This used to be there. I'll take care of the one second. What is that? What is that? This room? EVT. This is BB's RT. Or an RT, N is given there. PRT. Does not matter. Use that. So this is here. In the PVT diagram. So this is actually how to show this. So remember what is important. To show graphically. This is the PVC. PV is active surface. What I tell you, by all states of the systematic unity, this is satisfied. So one more. So you consider process. And best is reversible process. I will discuss the next topic is reversible process. But I have considered to explain this part. I can leave this at this stage. I will explain further. So you consider process. Okay. On this. Cut paper. There, straight. Oh, why I should borrow? Okay. So this, I used to have this. This is the plane. This is a system is here. Start one, state one. State P1, P1, T. You may consider as a number. I have to consider some. P1, P1, T. State one. Now I can carry out the process. They call it reversible process. Just to consider 1 to 2. System is uniform 1 to 2. Always lying on the surface means always satisfying T is these points are as long as when it is on this surface it is at equilibrium also, and that's why I consider reversible process. But don't worry. So all points. So there are showing reversible, don't worry. Reversible process. So system is taking from 1 to 2 along the surface. See, along the surface. Hey, God. So each state is satisfying exactly. On this very well. So this is 1, 2. So what is this? Suppose if I isothermal process, right? Isothermal process. How the center state will be no greater P1, P2, P2. So there are many intermediate ones, many numerous, infinite. So this is satisfying what? P is active. What is that? P1 is active. This is satisfying. P2 is active. This is P3 is active. P4, P5. Infinite. All states are satisfied. This is equation of state. Now I will do something else. This is on this paper. I am drawing. This is shown here. This is this car. Yeah. I will have to give projection of this. I will give the projection of this car on the surface. The line on the surface onto the PV plane, PT plane, and TV plane. This I will do next. So I have to remove this quickly. This is the last job you can do. Time boundary. Okay. And remove this all elements. It is actually projection. Can I do it here? That is the result of it. Let me try. Then I will try. Okay. Try. I'm taking the projection on wire. Come on. Try. Shake that. I give projection one. This is on the P plane. It is at the surface, right? It is at the surface. Oh, yeah. Right?